Okay, let's start today's seminar. The speaker is Giacomo Cacciapaglia from IP2I, Lyon. We'll talk about can massive graviton be ideal FIMP dark matter candidates? Please start.
Okay, so I would like to thank you again for the invitation. It's really nice to be able to give a seminar at these times, even if it's long distance. So, like you said, today we'll talk about the possibility that massive gravitons can be feebly interacting massive particles. So they can basically be produced via freezing during the early universe and play the role of dark matter. Now here, I want to make it clear since the beginning. So first of all, this is work I've been doing with Sungjun Lee and Ha-Yin Kai in Korea University. So they are not far from you. So first I want to clarify one point. When I talk about massive gravitons, I'm really not thinking about the mediators of gravity. So those are not models where if you want the ordinary graviton as a mass, but they're really models where there are additional, on top of the standard massless graviton, there are additional states that have spin 2 and they have a mass. So this is what I will mean by massive gravitons in the rest of the talk. But they're not really the mediators of the standard gravity. Now, this question is interesting because, massive gravitons typically they interact with an interaction strength that is of the order of the Planck scale, so the order of gravitational interactions. So certainly it's a very, very feeble interaction. And the point is that this is typically too feeble for these particles to be able to be produced in the early universe. So if you just take at face value the typical cross sections you would expect, you will say, well, there's no hope. The production rates are so small that you cannot even hope to fulfill, to completely saturate the dark matter element density. However, spoiler alert, why do we wrote this paper? Because at the end we found that this is not exactly correct. There are some enhancements that were never detailed before that can actually undo this kind of reasoning, and this will be the main message of this talk. But let me start with, okay, it's not moving anymore. Okay. Let me start with a very quick introduction because I'm sure you all know what dark matter is. Well, I don't, but if you know, that's good for you. But dark matter is basically something that basically constitutes 25% of the universe today. And this has been what I find particularly amazing about the problem of dark matter is that this is not an observation that we've been doing in a single context. In fact, we have evidence for dark matter in many different observations that range from astrophysics, a very low energy, so at the level of, I should say very small scales, at the level of a galaxy, as you well know, up to going to much bigger scales where you look at clusters of galaxies. This is done via gravitational lensing. This is just a photo I found on the NASA website. And we also have evidence by studying the properties of the universe in general, so the cosmological evolution of the universe. As you well know, dark matter plays an important role in explaining the acoustic oscillations that we observe in the cosmic microwave background. So it's really intriguing that observations done at very different scales with very different techniques, they all point towards the presence of some matter, because we know it has to be massive, some matter that is not interacting a lot to the standard model via light or strong interactions, but yet is the dominant component of matter in the universe. Actually, you can also see that this kind of sort of ratio scale, so the fact that you need more dark matter than ordinary matter, you can verify that this is true at the level of the galaxies, as well as the level of cluster of galaxies and the universe, the whole universe that we know. Now, the problem with this observation is that, well, it's telling us that something is there, something is happening, but it's not telling at all what it is that it's happening. All we need is something that is massive and interacts at least gravitationally with the other particles that we know of. So this also implies that we don't have any idea what the mass of the dark matter should be. In fact, there have been many models that have been proposed, and the kind of masses range, cover a very large mass range. You can have candidates that are, for example, axion-like particles that can be extremely small, even many orders of magnitude below the electron volt. There is a typical, sweet spot of the WIMP that has been studied a lot for a long time until, started having some issues with observations. So this is around the electroweak scale, so GV, TV or so. You can also think of extending this range to lower energies. And then you can go extreme and think of extremely massive, fairly massive objects like primordial black holes. So this is really an illustration to say that we are, looking for something dark in the dark. So we don't know exactly where to look for. So another point that I want to make, and again, I'm sure you're very familiar with, is the fact that the models that were very popular at the beginning of the search for dark matter, like WIMP, like weakly interactive massive particles, are now under some tension. So they're not completely excluded. This is, it's far to say that. But if you think of direct detection, there has been a huge progress in the past years. So this is just a summary plot with a lot of experiments. You see that, the current experiments, also the Panda X that released some data recently, are starting to probe quite an important part of the parameter space in the, let's say, with the WIMP sweet spot, so the scale that goes from the GV up to several TeV. And in fact, the future project will even probe the parameter space all the way down to the neutrino floor. And of course, we cannot go beyond that, because then we have signal coming from neutrinos, and that will completely swamp the potential signal from dark matter. So the point again here is that, there are very strong constraints from observation. And this is particularly true for particles that have some interactions with the standard model. So this is the case of WIMPs, and WIMPs are produced in the early universe via thermalization. So for this kind of dark matter candidates, you need substantial couplings to the standard model in order for these new particles to thermalize with the standard model bath. And then when at some point when the temperature reaches typically fractions of the mass of the dark matter will freeze out, so will decouple from the thermal bath, and the number of dark matter particles you have at that moment will just remain, because they are frozen to the value they have at that point. Now, another possibility that is also very intriguing is to think of particles that are extremely weakly coupled. Now, if the coupling is much, much smaller than the standard model, the typical weak standard model couplings, what happens is that this new particle, this dark matter candidate, will never be able to thermalize with the standard model path. Okay. So first of all, if the coupling is very small, you avoid all the strong direct detection probes, like the one I showed you before. So direct detection on Earth, this is not an issue anymore. However, we need to think of a new way to produce them, right? And the way here they're produced is that, even though the coupling is very, very small, during the early universe, there will be processes or interactions between the standard model particles that produce this new very weakly interacting particle. And once they are produced, they just remain there, because interactions with all the other particles in the universe is so small that they will not be destroyed by any other interactions. So now you see the philosophy is a bit different. So if you think of the WIMP, what happens is that their abundance is in thermal equilibrium with the standard model. So in this schematic plot, basically the standard model thermal density is given by the black line. So these WIMPs, so these thermal dark matter candidates will just follow this line. So their number density will also be determined by the thermal history of the universe, or by the temperature at a given time. And then at some point, when the universe expands, the temperature drops. So the relic density also drops following the expansion of the universe. At some point indicated by where this solid color line leave the black line, at some point there is the decoupling, and the relic density of this dark matter candidate will stop following the drop in the thermal relic density. So this is again the paradigm that was behind this, the WIMP. Okay, and again, let me stress to you again, you need some coupling with the standard model in order for this mechanism to work. Also, another well-known fact is that the larger is the coupling, the smaller is the relic density you will get. Why? Because of course, if you are more strongly coupled, you decouple later, and as you decouple it with a lower temperature, the relic density at the end of the day, at the end of the process, will be smaller. Now, the interesting point is that, okay, if you decrease the coupling too much, at some point you will not be able to produce enough relic density, right? There will not be enough strength to produce it. Now the question, the issue is that if you decrease the coupling so much that these particles will not be in thermal equilibrium at all, then this whole mechanism stop working. So there will not be any dark matter in the early universe, because again, they are not produced via thermal interactions. So you basically start with zero number of new particles, not with a number that is in tune with the thermal density. But what happens is that there will be processes that are typically scattering between standard model that produce the new state, or decays of some other heavy particles that are not really, that are thermalized with the standard model. And these processes will produce new particles. These new particles are long-lived enough or stable, and so they will just accumulate in the universe. So this is the FIMP paradigm that is illustrated by the dashed lines. So you see, contrary to the WIMP, what happens is that you start from very small numbers, 0, the reheating temperature, for example, and then you start building up a relic density. At some point you reach temperatures that are of the order, again, of the order of the mass of this new particle, the FIMP, and the mechanism that produce these new particles will start being dumping, because you don't have enough energy in the thermal bath to produce very heavy particles. And once again, the relic density will just freeze. And now we call it freezing, because instead of leaving the thermal bath, you're sort of building up, coming. So the new particles are produced by the thermal bath, but without ever thermalizing. Now, the behavior of this relic density is inverse compared to the WIMP case, in the sense that the larger is the coupling, the more of these particles you will have the more of these particles will be produced in the early universe. So now, if you imagine basically making a plot of the relic density as a function of a generic coupling, you see that there are two interesting regions, one with very small couplings, where you can do this FIMP mechanism, and one with very large couplings, where the WIMP will be active. In between, you don't have any mechanism that can produce enough dark matter, okay, in terms of a particle. So this is the generic scenario. Now, as I told you at the beginning, with the graviton, of course, we are interested in the FIMP part, because the couplings will be naturally extremely weak, because they are suppressed by the Planck scale. Now, there is another important feature of the FIMP mechanism that is related to the origin of the couplings. And the point is very simple, actually, to understand. If you think of a model where the coupling is renormalizable, so typically the amplitude square related to the process that will generate the relic density of the FIMP during the universe will be roughly constant. So thinking here the high energy limit, so where you can just neglect all the masses, and that's the naive estimate, just a constant, right? Now, why is this important? Because, well, if the process roughly remains constant independently of the temperature, you see, you start producing these new particles at the beginning, and but the number of particles produced at the beginning of the history of the universe will be relatively small compared to the ones produced towards the end, right? Where you approach the lower end edge of the freezing window. So basically what you learn from this is that typically renormalizable models are infrared dominated. So the number, so the final density of FIMP will depend crucially on the mass of the FIMP, so the closure of the window, the relevant window in temperature, but will not depend a lot on the initial condition, right? On when you start producing these particles. So when do you start producing these particles? This typically will be at the end of inflation, right? So there is a scale there that we don't know anything about. Well, we know very little about. We don't know what that scale is precisely. So this is good. It's a positive point because you can really be more predictive, right? You don't need to know the details of the inflation in order to calculate what's the relic density of the FIMP today. On the contrary, if you think of a theory with non-renormalizable interactions, typically the coupling of the FIMP to the standard model will be suppressed by scale lambda because of the non-renormalizable nature of the coupling, and the amplitude to compensate for this scale will be proportional to the energy, right? So that means that at higher temperature you have larger cross sections, and then the cross section drops where you go towards the infrared. This implies that in this case the production will be UV dominated. So if you want to calculate the relic density today of the FIMP, this will depend crucially on the value of the reheating temperature at the end of inflation. So basically the temperature where you start effectively producing these new particles. This is a bit of a problem because it sort of makes the prediction less solid. Okay, you can understand that, because it depends on details of the physics that are less under control. Now, again, a little spoiler alert, because if you think about the massive gravitons, so this is exactly falling into the non-renormalizable interaction case, because the gravity interactions are suppressed by scale, which is a Planck mass, right? So now you see two problems with the massive graviton. One is that, well, the coupling is too small because the scale is really large, it's the Planck scale. And the other one is that the production is sensitive to the reheating scale, basically. So to the scale where you start producing these new particles. So let me illustrate this by taking an explicit example. So this is some work that's been done by I think it's here in this paper by Lyon and collaborators. So the idea is to take a generic spin-2 particle, we'll call it Gn in the following, and couple it gravitationally with the stress energy tensor of the standard model. Okay, like graviton would couple in the standard gravitational interactions, with some coupling strength Ch, which is because this operator is dimension 5, is suppressed by scale that will be of the order of the Planck scale. Okay. So like I said, the freezing process will be inevitably UV dominated, so it depends on the reheating temperature, and the coupling is very small. This is a generic problem with this kind of model. So this has been studied by these people, by Lyon and collaborators.
I'm sorry?
And in particular, they look at, yes?
What's the small n in the Lagrangian?
Well, here I'm generically thinking of an extra-dimensional model. So actually, this is what these people were looking at. So it's a Kaluza-Klein gravitons from a flat extra dimension. So you should think of n as a label that indicates the Kaluza-Klein level.
Okay.
Okay. So G0 is basically the standard, it's not standard model, but it is the ordinary massless graviton, and Gn will be massive gravitons that appear in the Kaluza-Klein theory. But I mean, this is actually something you can generalize to any kind of massive spin-2 particle. This doesn't need to be necessarily a Kaluza-Klein graviton. Yeah.
This G is canonically normalized one, or?
Sorry, can you say that again?
This G field is canonically normalized field. I mean, I don't know why. Okay. Thank you.
Yeah. it just indicates a generic coupling of this spin 2 particles particle G with the standard model. Okay, so taking this Lagrangian, one can in the model these people studied, on top of this Lagrangian, they also assume that well, this state is coming from a flat extra dimension, and in that case this is important because you need to make the graviton stable. Okay, and in order to do that, they focus on a model where there is a parity that makes sure that the Kaluza-Klein states with an odd number are stable, so they cannot decay directly into standard model. So this already tells you that, well, here you can only have G2, you cannot have G1, because this will be direct coupling. Okay, of this new state to a pair of standard model particles. Now they computed the relic density. This will come typically from a 2-to-2 process where two standard model particles collide and produce two of these gravitons. And what they found that, well, depending on some parameters, we don't go too much into the details of that, you can get the correct relic density. This is along these solid lines, the diagonal solid lines. Gamma is a parameter that controls the reheating, what is it? So effective is the reheating after inflation. So basically, bearing this parameter, you see that you can more or less get the correct relic density, but you see you need in the vertical axis, you need masses for this, for the first Kaluza-Klein state. So this will be the typical dark matter candidate, to be of the order of the Planck mass. So there can be maybe a few orders of magnitude below the Planck mass, but not too much. Okay. And also there's an exclusion here that comes from cosmology, from the tensor to scalar ratio. So there is also an upper bound on the mass. The message I want to convey with this study, with this plot, is that, you know, if you really just want to take the model as face value, there are basically two issues. One is the one here, so the fact that you need to stabilize this new state. So specifically here is done with the Kaluza-Klein parity. And the other issue is that, like I was saying, the interaction is so small that typically in order to get enough relic density, you need the mass to be very large. And this also feeds back into the problem of the lifetime, because as you can understand, the larger is the mass of this new state, the smaller is the lifetime, right? So sorry, not the smaller, the smaller is the lifetime because you have a larger width, okay? So you are basically in the situation where you need to do something to stabilize this new particle, and you need to have the mass so large in order to be able to fulfill the relic density. So this is the generic situation we're in. Okay. So now the question is, what happens if, on the other hand, we want to consider very light gravitons? So, the theory that I was telling you before is really a theory that you can think of connected to string theory, to gut scales, to very high scales, where we don't know the physics very well. I mean, we don't have direct probes of that. What if we consider a very light state? Well, this is what we did in our paper. So the kind of interaction is the same I showed you before. Now again, this Gn, you can think of it as a Kaluza-Klein graviton. If n goes from 1 to 3 and so on, you can just add one of them, G1, and say, okay, this is just a spin 2 particle, okay, that couples to the standard model in this way with a given strength CH that will be determined by the physiology. Now we consider many processes. Let me start with this process where we produce a single one of this G by scattering two quarks, and they go into a gluon plus a graviton. Now, if you consider the graviton very light, so if you basically neglect its mass compared to the energy, and you also consider massless quarks, a calculation of the amplitude square for this process gives this result. So you see, as expected, is proportional to this coupling here, and because of this coupling carrying some dimensional mass, you have the energy appearing here in the numerator. So this is a process that, as expected, grows with the energy, therefore will lead to production of this new spin 2 state that is illuminated by the infrared. Okay, illuminated by what happens at the beginning of at the end of inflation. Now, this is the main result of the paper. What we found is that if you actually calculate the same amplitude, but now including the mass of the quark, the result is dramatically different. In fact, you see that there is a factor mq over mg square that appears in the amplitude square. Okay. Now, if you, of course, mg is very large, like considering in the previous example, this is irrelevant, right? Because it will be suppressed by a very heavy scale, very large scale. It's even a subleading correction compared to, well, if the mass is of order Planck, this is higher order in the Planck mass, if you wish, because you have a CH and also this 1 over mg to the 4th, the massive graviton mass to the 4th. Now, the point is that if the graviton, on the other hand, is very light, so much lighter than the typical mass of the standard model quarks, this acts as an enhancement. Okay, so compared to this result on the left, this will add the factor in q over mg to the 4th, sorry, because there is also this other term, and make the cross section much larger than you would naively expect. And what's also very interesting is the fact that this kind of enhancement is only applicable below the electroweak phase transition, because above the electroweak phase transition, all the standard model fermions are massless. So the result on the left will apply. Below the electroweak phase transition, then the result to the right will apply. So this is the main result. So this main conclusion of our study basically is that if you consider also the masses of the standard model particles produced below the electroweak phase transition, the cross section is actually much larger than you would expect, and this might dominate the whole production of the gravitons of the spin 2 particles. Okay, and this is what I will show you in a while. It actually works. But before that, let's try to understand where this enhancement is actually coming from, because it was very surprising for us too. So first of all, if you want to quantify this enhancement, think of the bottom quark. This is the heaviest standard model fermion that will be in thermal equilibrium below the electroweak phase transition. The top is a bit too heavy for that. So if you consider gravitons with a mass of around 2 MeV, and you will see why this in a moment, why this is the right scale, this ratio to the 4th is basically 10 to the 12. So you see, this is really a huge enhancement. So you can, a very tiny cross section suppressed by the Planck mass can be made not so tiny because of these kind of factors. So this is already going in a very hopeful direction. So where is this coming from? It's actually coming from the longitudinal degree of freedom of the massive graviton. And the way to understand is that if you think of, well, what comes out of the sum over all the graviton polarizations, where you calculate the amplitude square, so this is given by this form, where P is given by the, well, the usual Minkowski metric, minus this term that encodes the properties of the longitudinal component of the graviton. Now, this is the culprit of this enhancement, because you see it gives the 1 over mg square that appears in the amplitude, and this kappa, so this momenta, will basically pick up the mass of the quark that appear in the process. So finally, is simply this factor that gives rise to this factor mq square over mg square in the amplitude, and when you square it, it gives you basically this to the 4th. Okay, it's as simple as that. You can do, of course, a complete calculation to get this result. So what other processes have this kind of enhancement? Actually, all the processes that involve a standard model fermion and a massless gauge boson. This is what we found. So together with this QQ bar going to gluon graviton, we also have processes like scattering of a quark to a gluon, giving a quark plus a graviton, and also with the antiquarks. So this is the formula for this other process. Now, in principle, you also have similar processes with the photon. So you can have scattering of leptons and quarks with a photon. However, well, we don't consider those in the numerical results because the coupling is much smaller, is the electroweak coupling. And so these processes will not be as important as the processes involving quarks. So the other thing I already mentioned is that, well, the heavier quarks contribute the most because of the mass enhancement. And genetically, in our case, because the electroweak phase transition will be around 100 GeV or so, the top is not expected to be in thermal equilibrium, so the dominant contribution will come from bottom and charm, basically. And this is what we included in our numerical estimate. Now, let me jump to the calculation of the relic density. So this is done by solving the Boltzmann equations, and this is the generic result for the number density of this new of the massive graviton. Now we call it infrared because in fact this is a contribution coming from the enhanced cross sections. So the cross section with this enhancement coming from the mass of the fermion. Now, because this is only active below the electroweak phase transition, when you integrate over the temperature, you integrate up to the critical temperature of the electroweak phase transition, which is again around 100 GeV scale. And you integrate also down to the QCD phase transition because, as you can understand, below the QCD phase transition, the quarks will confine. So this kind of process will not be active anymore again. There might be other contribution coming from, mesons, but okay, we didn't consider that. So even though the window of integration between temperatures is fairly small, the fact that you have this huge enhancement up to 10 to the 12, as I showed you, is enough actually to make this this relic density competitive, actually, large enough to saturate the dark matter relic density. So you can do this integral numerically, and the final result is here, shown here. So you have that the contribution to the dark matter relic density coming from these processes is of this order here. Now, if you plug in the Planck scale for the coupling CH, you see that you can check that the typical mass that you need here is of the order of MeV, like I showed you before. Now, this looks cool, but it's not the end of the story, because in fact, as we do not add any Kaluza-Klein parity or any parity whatsoever to protect the graviton from decays, if you go back to the Lagrangian, this kind of couplings will also mediate decays of the graviton into standard model particles. Okay, so we need to worry about the lifetime of this Kaluza-Klein graviton. So this is not enough to celebrate and say, okay, we are done. We get the massive graviton dark matter. So for scales around MeV, the process is, so this graviton can decay into basic electrons, neutrinos, and photons. So we calculated the generic partial width, and now you see this is proportional to the same CH factor, but it's also proportional to positive powers of the mass of the graviton. And this is the issue. If the graviton is very small, then the width is very small. And if the graviton is very big, very heavy, then this width will be large enough that the graviton will decay fast and basically be excluded by, well, the fact that it's not cosmologically stable, and also by the fact that there are constraints on the decay products of the graviton, especially as here you see photons. Those will generate distortions in the CMB that are being looked for, and also indirect detection via diffuse gamma ray background. Okay. So from these papers, we saw that the typical bound on the lifetime of these new particles that decay in the universe is 10 to 27 seconds. So we impose these bounds on this cross section, on this width. And because basically the dependence on CH is the same as the one appearing in the omega here in the relic density, you can combine the two and write basically an upper bound on the relic density that you get by imposing this kind of constraint. And this is the final result. And as you see with the numerical adjustment we did, if the lifetime exactly saturates the bound, so is equal to 10 to the 27 seconds, the mass of the graviton that allows to obtain the correct relic density is 1.6 MeV. Now here in this plot, I showed the same kind of information, but now divided, you see in mass of the graviton versus the coupling 1 over CH, so the inverse of the coupling. The red line is the line where the lifetime saturates the bound coming from CMB and diffuse gamma ray background. I see that all the region below is excluded because it will give rise to too small lifetime for the state, for the graviton. On the other hand, the blue line represents the result for the relic density. It is an orthogonal behavior as you would expect because this decreases with the mass. And now the region below is again excluded because it will give rise to too much relic density in the graviton. So finally, the region that remains allowed is this one, the white one, where the blue line represents the points where the relic density completely saturates the dark matter relic density today. Okay. So another thing that you may ask, sorry, I forgot to put it in the slides, is what about the UV contribution? Because, well, there is, so first, before going to that, forgot to say this basically, the blue line highlights was the typical range for the masses. You see, it has to be maximum 1.6 MeV, but it can go smaller at the price of, well, increasing the scale that suppresses the interactions with the standard model. So this 1/CH. We also,
one question.
Yeah.
You were looking at the bounds on the lifetime from the diffuse gamma ray background.
Yeah.
But if you have something in the MeV range and you have a decay to 2 photons, in principle, you could also, if the particles are more or less at rest, could get photon lines, so to speak. Just a 2-body decay, so this would give you photon lines. Did you look into that at all?
We need to go back and look at these papers because we took the bound from those.
Okay.
So I'm not sure.
No, I'm just thinking if you have something around 500 keV, this would fit quite well if this if the particles are at rest. So this would depend on the velocity distribution of the particles, and also if the decay is strong enough to give you a line. I was just wondering whether you looked at it.
Yeah, no, we didn't look into that specifically.
Okay.
But I mean, I would say generic, I mean, the decays are very, very slow anyway. So I'm not sure there will be enough signal. But I don't know, we didn't look into that. So it's an interesting point.
Okay, thanks.
Okay. So yeah, I was saying the other thing we checked is the, in this range was the contribution from the UV production. So basically the production above the electroweak phase transition. And by quick calculation, we checked that actually this is many, many orders of magnitude below this contribution coming from the infrared. So this is really going in the direction of what I promised at the beginning, that, you know, this new effect we discovered allows to, first of all, enhance the production, the overall production of these massive gravitons. And second, to also limit, basically, so generates a natural UV cutoff for the calculation that is a well-known scale, physics scale, which is the one related to the electroweak phase transition. Okay, so the summary so far, the take-home message, and again, this is very general because we didn't take any specific model. We were really very generic in just writing effective couplings of a spin-2 particle with a standard model. This could be a graviton, could be a glue ball, could be a lot of stuff. I mean, any just spin-2 particle. This chiral enhancement is always there. Involves standard model fermions and one massless gauge boson, typically. And there is also a little enhancement with the Higgs, but that's less important. And the presence of this enhancement, as I said, again, allows to increase the production and naturally cut it off, so that is dominated by electroweak scale physics. And the typical mass is order of MeV at the most, okay, to saturate the relic density. Now, the next question we asked is, well, can we think of a model, of a complete model that can actually generate this kind of physics? And the model we found more apt to do this is extra-dimensional models where the spin-2 particles arise as Kaluza-Klein states. And in particular, we look at this model proposed by Agashi et al. And some other people previously, where you have a warped extra dimension with basically a brane in the middle. Okay. So the idea here, if you're familiar with this, the idea of a warped extra dimension is to have basically a space which is curved, and the curvature allows to separate basically the physics related to gravity, which is mostly localized localized on this end of the space, where the warping acts as a tuning of the typical mass scales. And here the typical mass scale is tuned up to the Planck scale. So this is the ordinary gravity part. And once you move inside the extra dimension, starting from here, the typical scales are tuned down. So they are warped down to lower scales, typically down to the infrared scale, which is the TV scale or the electric scale, if you wish. Now, if you just stop here to the middle brane, where the standard model is expected to be localized, what happens is that the zero mode, so the standard graviton, will be localized on the UV brane. The standard model states will be localized around the middle brane. And this allows to explain why gravity is so weak, because basically the overlap between these wave functions is very small. Now, the issue is that the massive gravitons will also typically, so if you ignore the part on the right, they will also be localized around this green brane, okay? So there will be a sizable overlap between the massive gravitons and the standard model. That means that, well, the coupling, the CH, is very large because it will not be Planck suppressed anymore, okay? That's why we need to consider a construction which is a bit more complicated. So it is a deeper infrared brane where the massive gravitons are actually localized. And in this way, the overlap between the ordinary matter and the massive gravitons is also suppressed. Okay, it's even typically more suppressed than the Planck scale because of the smaller wave function here. This is basically the main motivation why we go into this three-brane configuration. So needless to say, the basic idea here is that, well, gravity propagates everywhere in the whole bulk. The standard model fermions are typically localized here. Okay, on the whole standard model is typically localized only in this side of the extra dimension between these two branes. Okay. So what's the difference between this complete setup and the one we considered before? Well, first of all, there is not a single massive graviton. There will be a tower of them because now we are in Kaluza-Klein theory. So, okay, we need to consider just more than one massive graviton. And the other difference is that typically these models also have a relatively light radion. This is a scalar degrees of freedom associated with the size of the extra dimension. So to complete the model, also need to consider the couplings of the radion with the standard model. But here we added the coupling to two photons, and also couplings between the radion and the other Kaluza-Klein gravitons. Okay, this is given by this generically by these couplings here. Now here there are three types of couplings, so the CH, CR, and CQ. And they're actually quite different because if you compute them in the explicit model, you see that CH is actually typically suppressed by scale that is of the order of Planck, or even smaller, larger than Planck. This again can be understood by the localization of the massive gravitons compared to the standard model particles. Okay, this is the original coupling we used in the generic model. This CR is about the couplings of the graviton to Kaluza-Klein states and one graviton. Those are important for the decays of the Kaluza-Klein gravitons, and this is also suppressed by the Planck scale. But then there are couplings like this between the radion and the gravitons that are not suppressed by the Planck scale. They are basically of the order of the infrared scale. This is because they are both basically localized around here. Okay, so couplings between Kaluza-Klein gravitons and the radion are typically unsuppressed. This is very important because this relative size will determine what decays are dominant between these states. And this is again crucial to determine which Kaluza-Klein gravitons are stable enough to play the role, to contribute to the dark matter. So you can separate, so this all depends, as you can imagine, on the mass of the radion, right? So you can think of three regimes. So in the first, the radion is lighter. So twice the mass of the radion is lighter than the lightest Kaluza-Klein graviton. This is actually not good because the presence of these couplings, so the coupling of one radion to two Kaluza-Klein gravitons, which is unsuppressed, will basically imply that all Kaluza-Klein graviton will decay very fast into radions. So here in this parameter region, there is no way the Kaluza-Klein graviton can be a dark matter candidate. Of course, one can use the radion to do the job here. Now, the second regime is where the mass of the radion, so twice the mass of the radion, is between the first and the second Kaluza-Klein mass. What happens here is that so the first graviton will be able to typically decay into a standard model graviton plus the radion. This is done via these interactions mediated by CR. So they're Planck suppressed. This is good. However, the G2 will be able to decay into 2 radions, and this will be a prompt decay. So in this case, basically only G1 can play the role of dark matter. So the plot on the right shows the lifetime of this G as a function of some parameters of the model. So this is the curvature times the radius of the second part of the space. And this model here, so the situation 2 corresponds to this pink line, okay, the dash pink line. And what you see clearly is that, here there is a kink because in this part of the plot, the decay of G1 into G0 plus R dominates, okay? So while here is mostly the case into standard model that dominates. So unsurprisingly, what happens in this mass regime is that the lifetime of the lightest graviton is shortened because of the presence of the radion. And now, so this is compared to the lifetime of the universe. If we want to fulfill the bounds we mentioned before, typically most of these parameter spaces could be ruled out. Okay, this depends on the decay of the radion, but okay, typically the radion will give photons, and again you have bounds from the CMB and the gamma indirect detection of via photons. So okay, maybe a little bit complicated, but the simple point is that while this is not very favorable because the lifetime of the lightest Kaluza-Klein graviton tends to be shortened by the presence of the radion. The third part is where the third kinematic region is where the mass of the radion is even larger, so twice the mass of the radion is larger than the second Kaluza-Klein mode. So if this is the case, then these 2 decays here are not allowed. That means that both G1 and G2 will be long-lived. And for G1, the only decays come from the direct couplings to the standard model, and the lifetime will follow this red line. Okay, and this is good because it leads to the longest lifetimes possible in this model. The G2 will also be stable, okay, because it will not be allowed to decay into 2 radions and is not heavy enough to decay into 2 G1s. However, the heaviest KK modes like G3, G4, and so on, they will be able to decay into 2 G1. Okay, so they decay fine. This is not suppressed by the Planck scale, and this will be fast enough to make them basically not a good dark matter candidate. So at the end of the day, we focus on this third case, kinematic regime, where we have 2 dark matter candidates, G1 and G2. Okay. So if you repeat the calculation and you project it into the parameter space of the model, so this again is the curvature times the 2 radii of the 2 patches of the extra dimension, this is the kind of picture that emerges. So there is a region below down here where the lifetime of G1 is too short to pass the bounds coming from, CMB and the photons. There is a region here where the relic density is too big. And this is, well, again, because you don't have enough, it's either the mass is too large or the coupling CH is too large. And then along this red line, this is where you get the correct relic density. So if you map the value of these parameters into the masses, you see that this corresponds to masses below roughly 2 MeV. So the mass scale is the same as what we obtained in the generic model. Of course, if you go down this way, the relic density decreases very quickly. So in this part, you will not be able to explain the full relic density, dark matter relic density with the gravitons. But this part of the model might still be viable if the radion is also stable somehow and can contribute to the relic density. Okay, so this is the final result for the extra-dimensional model. And now I guess what I'm left with is just summary. So the main point of this work was to basically reevaluate the production of the massive gravitons as FIMPs, as freezing dark matter particles. And what we discovered, surprisingly, is that there is a chiral enhancement below the 2-week breaking scale. And this has two good benefits. That, again, is the most important point of our work, most important result from our work. One is that the freezing is dominated by the electroweak scale, not by the inflation scale or the heating scale. And the other one is that the enhancement allows very light gravitons, as light as 2 MeV roughly, to produce the correct relic density. And this again applies not only to actual gravitons, I mean, they come from hexadimensional theories, for example, but to a general class of spin-2 particles, as long as they couple with a strength that is of the order, at least of the order of the Planck scale. This is it, and thank you again for your attention.
Thank you very much for the nice talk. Let's open it up for question and discussion. Any question? I have, please.
I had one question concerning the model. You're looking at a setup where you basically have one throat with 2 branes.
Yeah.
Would it in principle work to take a UV brane and take matter into one setup and then via boundary conditions couple it to another setup which is deeper, where you just have your additional KK gravitons? So doing it as a 2 throat setup, so to speak.
So you're thinking of 2 throats glued on the UV?
Yes, with one throat where you just have the standard model and matter, and a deeper throat in which you just have gravity propagating, such that you have lighter KK gravity modes, which couple to the IR brane only via basically mixing with contact interactions on the UV brane.
Yeah, I guess it might work. Yeah.
Because this is something which might be easier to realize from a D-brane setup in some way.
Yeah, I don't see any counterindication, let's say, to the kind of construction. So definitely, yes.
It could give you a smaller coupling of the IR brane of the standard model throat to the lightest KK gravitons, but it might be.
It comes via mixing.
Yeah.
Well, but that's not an issue because, well, if you look at the simple case, simple calculation, you typically need a suppression that is, larger than the Planck scale. I mean, this is basically the scale appearing in CH in GV. So
yeah,
there might even be a good feature. Open up more the parameter space. So yeah, looks like a good model for this. I
have many more questions, but I think I leave them.
Maybe one. Thomas, one thing to watch out will be the mass of the radion, because in the case, I don't know how many radions there will be. Being 2 separate branes, there might be two different radions, and one is to watch out that maybe the radion is too light, then the gravitons will decay into radions.
Yeah. Yeah. I'll wait with other questions and let others ask first.
Any other questions? I have one really nice question. So, so you are considering 2 MeV the spin-2 particle, right? So
yeah, in the hexadimensional construction, yes.
Why can we not detect that particle in LHC or something? I mean, it also.
Yeah.
Also, a couple with standard model and quite light.
Yeah, it's true they're very light, but okay, what do I have? Sorry, no, okay. It's here too. It's true that they're very light and decouple via this kind of interaction to directly to the standard model. However, remember that this interaction is suppressed by the Planck scale. So this is really gravitational strength interaction. So producing them at the LHC will be fairly suppressed. I expect cross sections that are too small to be detected at the LHC. Of course, I mean, I should say that there are things that maybe can be done, and with Sung and Lyon, we are thinking about it now, but we don't have any result yet. What we are thinking is to use the chiral enhancement actually to have a collider situation where you have enough cross sections. But I think that to be able to detect them, you need to collide heavy-ish particles. So the quarks in the proton and the gluons will not do the job because they don't have this enhancement. And you need a very clean environment because the signal will be extremely, the cross-section will be extremely small. So you need a very clean environment where you can detect the presence of these, of these kind of particles. And the other thing is that, here is the dark matter, we have only two states. So the first two Kaluza line. But as the mass is so small, if you go to in a collider environment, you will be able to produce many more Kaluza-Klein states. So this is also one effect that might enhance a little bit the cross-section. But I don't know if this is enough. We haven't done any estimate yet. So to wrap up on the answer, I think that the LHC probably is hopeless. But we're really thinking about future colliders, like muon collider, something along those lines.
Okay, thank you very much. Any other questions?
Can I ask one thing concerning the colliders? Because if you're thinking about MEV scales, would it be possible to do something with high power lasers, for example, using the photon coupling? Thinking of things similar to what is done at DESY for ALP searches.
Yeah, it depends on the scale because here we're really at the Planck, so
yeah, okay.
I'm afraid the cross section will be too small. And again, if you just collide lasers, there will be no enhancement.
Okay.
So my feeling is that the only hope is to be in a situation where you can use the chiral enhancement to get a larger signal. So ideally, I would collide a photon to a big quark, right? But unfortunately, we don't have a big quark beam we can use. But photon seems to be.
I see.
I'm not very hopeful with that.
And one question concerning the. So is this a cold dark matter candidate? I.e., did you look at the velocity distribution of the dark matter you get out of this? Because you have a mass of MEV, and you determined where the major production, or at which energy scale the major production is taking place. So I guess one could calculate the rough velocity distribution from of the dark matter from this.
Yeah, I think the velocity is the standard one from FIMPs, because I mean they're produced at different temperatures, but then they follow also the expansion of the universe, for what I understand. So I think that if you think about the velocity and the type of dark matter, we can just take as a reference the standard FIMPs. And I think in that case, if I remember well, there is a window where they are considered as warm dark matter. And this is between roughly 1 keV to 100 keV. So I would say that, you know, if you're really around MeV, that's probably is going to be a cold dark matter candidate.
Okay.
If you are a bit below, down to 1 keV, then it's going to be warm dark matter. Below 1 keV is probably going to be a hot dark matter, which is disfavored at the moment.
I see. So the fact that you have your main production around the QCD scale is not shifting the standard FIMP argument.
The electroweak, no, I don't think so.
Okay. I see. Thanks.
I have one question. So you consider the basically QCD sector, QQ going to, and how about the electroweak sector or Higgs sector?
So
they don't have a chirality enhancement problem.
So no, there is a chirality, a chiral enhancement with leptons. So you can think of a process with sorry, what is the process? Instead of quarks, well, you also have quarks, but you can just replace the gluon with a photon. So this will also be active for leptons, and they will not be cut off by the QCD phase transition. However, the coupling is much smaller. And the production is still dominated, you know, around the electroweak phase transition, and then it will be less important when the temperature goes down. So I think that typically the contribution of the say the electroweak process, well, the photon, the electromagnetic processes will be less important. I think for the Higgs too, because of the mass of the Higgs, you will lose this very quickly. I mean, the Higgs will not be, will likely not be in thermal equilibrium, you know, for a long time below the electroweak phase transition. That's what we expect.
Okay. Okay. Yeah. Right. Thank you.
Any other questions? I also have one more naive question. So, I mean, if we considering the, I mean, UV completion of gravity, such a light KK mode can be dangerous in the context of unitarity, I think. So my question is, your UV embed is also kind of IR-EFT in the context of the UV completion of gravity, right? So you think you can UV complete this model to kind of string theory or something?
This kind of model?
Yeah, yeah.
Well, I'm sorry to say I'm not really an expert of, you know, gravity and UV completions of gravity, but my understanding is that yes, I mean, this kind of extra-dimensional setups can be obtained in string theory. And because of the warping, typically, so you can think of this as an effective theory, but typically if you want the cutoff of this effective theory is really the Planck mass, because it's dominated by the UV. But it depends on what processes you are looking at. But I think typically gravitational processes will be cut off by the UV scale, so the Planck scale. And also Thomas gave another example where you have two throats that are glued on the UV, and that's also something you can obtain from string theory. So again, as a non-expert, really, my impression is that it's usually not a problem.
I see.
These kind of models have been proposed many times, where you have very light, you know, Kaluza-Klein gravitons, but the theory is still sort of, you can think of it, you can think the effective cutoff to be the Planck scale.
Okay. Any other questions? I see no more questions. Then let's thank speakers. Thank you very much for the nice talk.
Thank you very much. Bye-bye.
Thanks to you for your attention.
Bye-bye.